Okay, ladies and gentlemen, welcome to this second lecture on logic and set theory. The first week was for you the first getting to know logic, propositional logic, and predicate logic. For us, it was definitely getting to learn the technicalities of Microsoft Teams, YouTube streaming. Making digital tests in ANS. I can tell you that was not easy, but I suppose you had a harder time making the exercises. Welcome to the second stream. What I want to do is I don't have too many Mentimeter polls today, unfortunately. I would have liked to have a couple more, but I didn't have time to produce them. But I do have a couple of questions for you to start with. So let me share actually my let me get myself out of the way. So if you go to www.menti.com, then please use code 9298428 to enter your, to fill out this little questionnaire about what you thought of the first weekly test. And was it feasible? Did you see the instructions, things like that? I would like to know so I have to have these things to get a bit in touch with what you're feeling. All right, there we go. Okay, there are still a couple of participants voting, so I'll wait some more time. This is sort of lengthy questionnaire, I realize. All right, ladies and gentlemen, and while you are actually entering your answers to this questionnaire about the first online weekly test, let me point out to you that we have Peter Lamboy watching the Canvas chat for you and relaying all your questions to me. So please, if you have questions during the lecture, do not hesitate to use the Canvas chat to ask them. I will not monitor the YouTube chat. So all questions should go via the Canvas chat, and please only post serious questions there, so that we can still see what needs to be answered. All right. I think the questionnaire in Mentimeter has stabilized a bit. So just let's comment a bit on the results. So fortunately, it's good to see that most of you actually carefully read the instructions for the online weekly tests, and that it was clear where to find the test. Also, quite a number of you indicate that they participated in the practice test. Well, I was a bit disappointed seeing that it was definitely not the majority of you who actually participated in the practice test, and I think that could have prevented a couple of problems that we saw today in the online weekly test. In particular, then you could have already practiced with uploading documents. You're sort of you are neutral about the statement online weekly test 1 was easy. I think I'm happy with 2.9 as a result. It means that you didn't find it excessively hard, at least the majority of you, but also not very easy. And this is the way it should be, I think. It should not be too easy, not be too hard. And you, well, not all of you indicate that they had sufficient time to upload their solutions, actually. So you have to keep this in mind. And I can imagine, especially that if you did not do the practice test, then it was probably it was new to you how to upload your solutions. You should get used to that. Fortunately, we have 6 more weekly tests to go. I'm sure you'll get the heck of it soon enough. You didn't too much appreciate being in the MS Teams meeting. We did that purely to have an easy access point for you to reach us in case of problems. We'll see how we whether this is actually necessary. Maybe we'll create larger meetings. I think the instructors that were present there could handle the load at the moment. Okay. I'm looking at my own private chat with Peter Lamboy to see whether there are any questions in the Canvas chat, and I see that there are no questions there that were worth relaying to me. So let's now continue with the lecture, and what we are going to do. Let me put myself again in the slide. What we are going to do is we're going to discuss a particular formal system to produce mathematical proofs. And we'll proceed in the spirit of this guy that we've already seen, Aristotle, who actually was the first to invent, who started to discuss abstract logical reasoning and really started to consider what are the valid rules of inference, so to speak. And basically what he said was, well, you have to study this subject, not worrying too much about what you are debating or what you're reasoning about. You should study the reasoning without being distracted by the content, basically. So you should abstract from that, and that's exactly what we have done in the past week. We have introduced abstract propositional logic, where we basically represented concrete statements like I open a bottle of wine, I will go and play tennis. We basically represented those by proposition variables, and then we basically could focus on the study of, well, if you have a conjunction of such things or a disjunction or an implication, what does that really mean, and how can you combine statements to form other statements, more complex propositions. And what we're going to see today is how you could reason about, or how you could formulate reasoning principles for such abstract propositions. All right. So to summarize, Aristotle said, well, first let's study the principles of logical reasoning in an abstract context, and that's also what we're going to do in an abstract context of propositional and predicate logic, and only later apply the general principles that we have formulated and that we are certain about then to prove statements about concrete things. And well, concrete you should here take with a pinch of salt, because we're going to talk about mathematical things, about sets and relations and functions and other mathematical notions. We're not so it's concrete in that sense of the word, but still we're going to first study what is a decent mathematical proof before we are actually going to prove something concretely. Okay, and this formal system is going to formalize by means of derivations the way we usually conduct logical reasonings. All right, let me start the first video in which basically introduces you to the topic. In this lecture, we will introduce the flag-style way of presenting mathematical proofs. We believe that presenting a proof in this way has the didactic advantage of clarifying the roles of the different elements in a proof, and moreover, it helps to structure the process of finding a proof. Let's consider the statement, for all integers x, if x is even, then so is x squared. we shall give a mathematical proof of this fact first, and then we shall rearrange the elements of that proof in such a way that it fits the flag style way of presenting it. It is good practice to first analyze the logical structure of the statement. Observe that it is a universally quantified implication. The statement quantifies universally over all integers x, and we need to establish for every integer x the implication if x is even, then the square of x is even. A mathematician knows a technique for proving universally quantified implications. It amounts to declaring a variable x, assuming that it is even, and then establish that x squared is even too. We shall discuss this technique in detail in a subsequent lecture, so please accept the correctness of this technique for now. What is happening here is that the original goal is simplified. We now need to prove that the square of x is even for some variable x, about which we have assumed that it is even. The next step is to realize what it means to say that x is even. It means that there exists another integer y, such that x is equal to 2 times y. Sort of implicitly, another integer y is declared. Then we may start to calculate. Starting from the square of x, we replace x by 2y, and then do some algebraic manipulations. It is important to realize that since y is an integer, so is 2y squared. Using that x squared is 2 times the integer 2y squared, we can now draw a final conclusion and reach our goal: x squared is even. Let's do an analysis of the logical structure of this proof. The statement for all x an integer, if x is even, then so is x squared, is the main goal of this proof. The first step of the proof achieves a simplification of the goal. A variable x is declared, it is assumed that x is even, and thereby the new goal becomes to prove that x squared is even. In the remaining steps, conclusions are drawn from the generated assumptions and already established facts, in order to reach the goal x squared is even. First, we use the assumption that x is even to declare another integer y such that x is equal to 2 times y. Then we draw a conclusion on the basis of mathematical calculation for x squared, using that x is equal to 2 times y. Then, since y is an integer, 2y squared is an integer too. And finally, we conclude that x squared is indeed even. To summarize, first we simplify the goal, and then we infer some conclusions from the assumptions, leading to the final conclusion that x squared is even. Now, for didactical purposes, it is convenient to rearrange the elements of the proof somewhat. We want to achieve that one can read a proof from top to bottom and always be sure that the statement is either an assumption or can be inferred from statements that appear above it. Note that the mathematical proof you see here does not satisfy this property. There is a statement x squared is even at the beginning of the proof, at the moment that it has not yet been established. And it's not an assumption either. It is also convenient to clearly mark declarations and assumptions as such. The first step, therefore, requires putting the new goal of the proof at the bottom and put the declarations and assumptions at the top. Assumptions and declarations are put in a flag, and the flagpole indicates the extent of their validity. Note that we can put the subsequent conclusions in the order in which they appear in the mathematical proof. Let's go through the construction of this proof once more, and then also add a few details in the process. The first step of the proof is to logically simplify the goal. And this generates a declaration, let x be an integer, and an assumption, suppose that x is even, and the new goal is to prove that x squared is even. Then we start to draw conclusions from facts that we have already established. In the first step, we draw a conclusion from the assumption that x is even. To explain this step in a bit more detail, here you see the definition of x is even. It involves the existential quantification over some integer y. This integer y is declared in the proof, and that's all. Then we do a calculation for x squared, using that x is equal to 2y. First, we replace the x in x squared by 2y. This is allowed because of the general mathematical fact that whenever u is equal to v, then also u squared is equal to v squared. As you can see, the next step involves quite some mathematical reasoning, which was left out because you are completely familiar with this type of calculation. It is high school material. Then we replace 4 by 2 times 2 and rearrange parentheses. Also, this is standard mathematical reasoning. Since y is an integer and both the operations of squaring an integer and multiplying an integer by 2 yield integers, we may conclude that 2 times 2y squared is also an integer. Finally, we can then draw the conclusion that x squared is even using the expression for x squared as 2 times 2y squared, and using that 2y squared is an integer. We apply again the mathematical definition of being even. In this case, x squared is even if there exists some integer such that x squared is equal to 2 times that integer. When presenting the proof for the statement for all integers x, if x is even, then so is x squared, we have omitted some details, as you have noticed. All mathematical proofs are like this. They present the crucial insight at a certain level of abstraction, taking for granted that the person to which the proof is addressed can fill in the details that are missing. In the next lectures, we will elaborate on how to construct Flag-style derivations, and then we'll focus not so much on mathematical content, but rather on the logical structure of proofs. So in particular, we are going to consider how to deal with implications, how to deal with universal quantifications, and how to deal with the other operations of predicate logic. Okay, ladies and gentlemen, I can imagine that that proof went too fast to really follow in detail. The actual contents of the proof here is not really what matters. What matters here is that we are going to present a way to construct mathematical proofs that is slightly different from what you've basically seen at the beginning of the video, where we produced it, or actually first wrote a proof in the style that mathematicians use. And well, the purpose of this way of writing the proof is that it will allow us to separate certain types of statements in a proof. And let me so what you should get from the video, at this moment, I suggest that you watch it later at leisure, and when you can also stop the video if something is going too fast. But what you should get from the video now is that there are these different kinds of statements in a mathematical proof that we want to treat differently in this system. I have two Mentimeter questions still about this. Let me show you here the Mentimeter screen. So the first question about this last video that you have seen is, which kind of statements are put in a flag? I'd like to see your answers to that. And so the questions that I'm now posing are basically refer to the main things that you should get from the video right now. And let me also promise you that I'll show a couple of videos, but I'll also do a couple of examples, two examples actually, during this lecture on my own Blackboard here, so that things develop a bit slower. All right, I'll give you a couple of more seconds to enter your answers. There's still answers coming in. All right, let me show you the results of the poll right away. There you are. So there are 4 types of statements in a proof. We distinguish goals. Goals are the things that the things that you want to prove. So and there are assumptions. So those are statements that you make when you're trying to prove your goals. There are conclusions that are drawn from previous statements in a flag style derivation, and there are variable declarations. Now, indeed, so there are 2 types of things that you put in flags in a flag style derivation. There are assumptions and there are variable declarations. Now, I should add to this that actually in the system that we're going to set up now, you are not going to raise flags simply because you want to state an assumption or declare a variable. It will not go that way. You will apply a rule. And that will become quite clear in a bit. First, let me ask you one more question. Close this poll now and move to the next question. So suppose that you want to prove a statement, then where do you write this statement? You want to prove a statement P. Where do you write this statement P in a flag style derivation? So should you write it at the top, somewhere in the middle of the derivation, or perhaps at the bottom of the derivation? Okay, I think I can give you, say, 15 seconds more. Okay, let me show you the results and also show you the correct answer. So goals you always write at the bottom of your derivation. So basically what we're going to do is this system of derivation will, in this way we create derivations from the bottom up upwards. So we're going to do, and so that you write your goals at the bottom. This will become, I suppose, very clear when we discuss the rules for implication and conjunction, and immediately also discuss an example pertaining to these rules. So I'll start the next video now. This video is introducing proof strategies for conjunction and implication. And after that, I'll introduce a second video in which we'll give an example of how to construct, how to prove that a certain abstract proposition involving implications and conjunctions is a tautology. There we go. In this lecture, we will present introduction and elimination rules for conjunction and implication. Let's first consider conjunction. We want rules that allow us to simplify the goal if our goal is to prove a conjunction, and we want rules that allow us to use a conjunction or to draw conclusions from it when we have already established it. Let's first concentrate on simplifying the goal if it's a conjunction. Note that a conjunction P and Q is true if both P and Q are true. So, to prove that a conjunction is true, it is enough to prove that both conjuncts are true. Let's formulate this general proof principle as a derivation rule. This rule applies when we want to establish a conjunction P and Q, and it appears on line N. And the rule works from bottom to top, as indicated by the arrow in the upper right corner. To prove P and Q, we have seen it suffices to prove both P and Q separately. So this rule allows us to introduce two new subgoals, one on line M and one on line N-1. And if we manage to prove both subgoals, then we may conclude with conjunction introduction on M and N-1 that the conjunction P and Q is true. The dots in the formulation of this rule indicate that the derivations for the subgoals P and Q still need to be supplied. We proceed to consider the situation that we have already established the conjunction P and Q, and we want to draw conclusions from it. As you can see from the truth table, if the conjunction P and Q is true, then so are its conjuncts P and Q. So we have the general principle, if we know that the conjunction is true, then we can conclude that both conjuncts are true. Let's turn this general principle into two derivation rules, one that allows us to conclude the left conjunct and one that allows us to conclude the right conjunct. Here we have two rules that apply when the conjunction P and Q occurs on line M in the middle of a derivation. The bars indicate that the conjunction P and Q is to be found in a part of the derivation that is already finished. And the arrow in the upper right corner of the rules indicate that this is for reasoning from top to bottom. Now suppose that we have established P and Q, then we have already seen we can draw two conclusions from this. We can conclude the left conjunct, but we can also conclude the right conjunct. And we indicate this by saying that there's a conjunction elimination on line M. Let's now consider implication. We want to have a rule that allows us to simplify a goal if it's an implication, and we want to have a rule that allows us to draw conclusions if we have already established an implication. Let's first consider the situation that we want to establish a goal and it's an implication. Note that an implication is true if either its condition P is false or its conclusion Q is true. Now, it is a bit difficult in a derivation to prove that something is false. The derivations are geared towards proving that things are true. So let's ignore the first line of the table for the moment, and then we may realize that actually it suffices to prove that Q is true if we want to establish that the implication P implies Q is true. So this gives rise to the following proof principle. To prove that an implication is true, it is enough to prove that its conclusion is true. Now, this proof principle is not really strong enough, as we will illustrate with an example. Consider the implication, if x is even, then so is x squared. Unfortunately, we cannot prove that x squared is even right away. In fact, it is not true in general. But we can prove that x squared is even if we may use that also x is even, and we have already seen a proof of that. So we can prove that the conclusion x squared is even is true using the assumption that also the condition x is even is true. So we can slightly modify our principle a bit, including the use of this assumption. So to prove that the implication is true, it is enough to prove that the conclusion is true under the assumption that its condition is true. Now, actually, this principle amounts to excluding the third row of the table, because there you see that the condition is true, but the conclusion is not. Let's formulate this principle as a derivation rule. This rule applies when we want to establish an implication P implies Q, and it appears on line N in our derivation, and the rule works from bottom to top. Remember that to prove the implication P implies Q, it suffices to establish the conclusion Q under the assumption that the condition P holds. So suppose that the assumption P appears on line M and the conclusion Q appears on line n-1, then we can apply implication introduction on M and n-1 and conclude the implication P implies Q. Note again that there are dots appearing in the formulation of this rule to indicate that we should still provide a decent derivation of the subgoal Q. And also the rule has a flag. Remember that we have agreed to indicate that certain statements in a proof are assumptions by putting them in the flag. You may notice that the flagpole runs until we apply the implication introduction. This is the moment where the scope of the assumption P ends. Let's proceed to present a rule that allows us to draw conclusions from an implication. Suppose that we only know that the implication P implies Q is true. Then from that fact alone we cannot yet conclude anything about P or Q. As you may notice from the truth table, it is still possible that P is true, but also that P is false. And similarly, it's still possible that Q is true, but also that Q is false. However, if in addition we know that the condition of the implication P is true, then we can draw a conclusion about Q. And this will be our proof principle. So if we know that the implication is true, and also its condition is true, then we may conclude that the conclusion is true as well. Let's formulate this principle also as a derivation rule. This rule applies when we have already established two formulas, P implies Q on line L and P on line M. It is not necessary that these formulas appear in this order. The implication may also have been derived after its left-hand side. If this is the case, then we can apply implication elimination on L and M and conclude that also the conclusion of the implication Q is true on line N. We have presented derivation rules for conjunction and implication. And we have distinguished two types of rules. Introduction rules, which allow us to logically simplify the goal of a derivation, and elimination rules, which allow us to infer conclusions from already established facts in a derivation. This concludes the presentation of the first 5 derivation rules. In the next lecture, we will give an example derivation using these rules. Okay, that was the second video for today, in which 4 derivation rules have been introduced. And you see them also here on the slide, and actually deliberately copied a page from the book. This is page 375 from your book, also to point out to you that there's a convenient table at the end of the book, the convenient collection of tables actually at the end of the book, where you can look up all the rules that you can apply when constructing derivations. And I urge you to have a look at that. If you don't have a book yet, then perhaps you remember that I have posted an announcement in Canvas also with the exercises from the book, but also in this there was a link to exactly these tables that you can find in the back of your book. So it's important that you, especially in the beginning when you do exercises, take these or make sure that you look at these rules to know what you can do. Basically, we have seen 4 rules. Let me briefly comment on them. So the introduction rules, we have a rule for conjunction introduction, and we have a rule for implication introduction. These rules allow you to prove either a conjunction or an implication, and these rules are applied from bottom to top. So you have your goals, if you remember, at the bottom of your derivation, and above this goal you should create a proof in this derivation of that particular goal. Now this rule for conjunction introduction says that if P and Q is your goal, is what you want to prove, then actually it is enough to prove P and Q separately. These dots here in the book are a typo, they should not be there. The idea is that these 3 dots indicate, okay, we simplify the goal to prove a conjunction here. We simplify it by saying, okay, it is enough in this case to prove these 2 goals separately. So it is enough to provide 2 separate derivations, one for P and one for Q, and the 3 dots are to symbolize that actually on these places you should still insert derivations for these goals. And similarly for the implication, so if your goal is to prove the implication P implies Q, then the rule says that then the rule says you assume P, the left-hand side of the implication, and thereby you simplify your goal. You simplify the original goal to prove the implication to actually proving Q in the context of this assumption P. Now those are the introduction rules. Those are rules that you apply when your goal is to prove a conjunction or an implication. If you want to use a conjunction or an implication, so suppose you're trying to prove some particular goal and you got thus far you only managed to prove a conjunction, then this elimination rule says that from this conjunction P and Q you may conclude P. You may also conclude Q. So these are actually two rules combined into one here. So you may conclude either conjunct from a conjunction. And here you see that there are you don't see three dots, but you see these bars here, and these are to symbolize not that there a derivation should be inserted there, but rather that actually there's already a derivation present of this P and Q. And this could also be some derivation that you need to do somehow, and then at some point later in the derivation you may conclude P because already you have established P and Q. And similarly, if you have a derivation already of P implies Q, and you somehow also manage to derive the left-hand side of the implication, then you can actually eliminate this implication, as we say, and conclude Q. So those are the four rules for implication, conjunction, and conjunction that we shall use. So again, introduction rules if you want to prove if the conjunction or the implication is your goal. Elimination rules if your conjunction or implication is something that you have already derived. Now, in the next video, we're going to see an example, but before we get to that, let me tell you something about the proof strategy, and I'll return to this after the video. So how do you construct a derivation for a certain formula, and this derivation is then to prove that the formula is a tautology? You follow the following strategy. You start by writing the goal and the formula that of which you want to prove that it is a tautology. You write it at the bottom. At the bottom of your derivation, at the bottom of your sheet, if you're doing an exercise. I always recommend using an entire sheet for one derivation. And then you start using introduction rules to logically simplify the goal. And these introduction rules they may, as the implication introduction rule does, may generate hypotheses, may generate flags, may generate assumptions. But this is the only way in which you can introduce flags in your proofs, by applications of introduction rules. Okay? And then when you have simplified your goal to the point that you cannot simplify it further, I mean, it has no recognizable logical structure anymore. It's a very simple thing. It's say a proposition variable or something else without logical structure. Then what you do is you use elimination rules, because then typically you have generated some hypothesis at the top of your derivation, and you start drawing conclusions from that. And drawing conclusions you do using elimination rules. All right, I'd like to, and later we'll refine this strategy a bit. I'd like you to keep this strategy in mind. I'll return to it after the video, but we're now going to see an example in which we construct by means of a derivation, a proof that a certain formula is a tautology. In the previous lecture, we have presented introduction and elimination rules for conjunction and implication. In this lecture, we will present an example showing how to construct a derivation using these rules. We shall prove that the formula P implies Q and R implies P implies Q and P implies R is a tautology. A derivation always starts by writing the goal at the bottom. Then it is an advisable strategy to first try and apply introduction rules in order to logically simplify the goal as much as we can. The goal at hand is an implication, so to simplify it, we should apply the implication introduction rule. Of course, we do not yet know how long our derivation will be, so for now we leave out the references to the line numbers.
The rule tells us to assume the left-hand side of the implication, here P implies Q and R, put it in a flag at the top of the derivation, and the right-hand side of the implication becomes the new simplified goal. Note that the assumption ends up on the first line of our derivation. We can therefore already fill in this line number. We now repeat the process with the new goal P implies Q and P implies R. It is a conjunction, so we apply the conjunction introduction rule. The rule tells us to prove both conjuncts separately. So we state the left conjunct as a new subgoal and also the right conjunct. Let us now first concentrate on the first subgoal P implies Q. The new subgoal is an implication, so we apply the implication introduction rule. We assume the left-hand side of the implication and get the right-hand side of the implication as our new goal. The goal Q cannot be simplified further, so now it is time to start drawing conclusions from the two assumptions we have made. The assumption on the first line is an implication. Let's check whether we can perhaps apply the elimination rule for implication. To apply implication elimination, we also need the left-hand side of the implication, which fortunately is available in the form of an assumption on line 2. By applying implication elimination, we may then infer the right-hand side of the implication. We need the left-hand side conjunct of the conjunction that we have just inferred, and we have a rule to get it. It is called conjunction elimination. Let's now also fill in some line numbers. We have now derived our first subgoal. But remember, we have a second subgoal to derive. The derivation of this subgoal will be very similar. It starts with an application of implication introduction. The new subgoal R cannot be simplified further. We should try to infer it from the assumptions on lines 1 and 6. Note that on line 1 we still have the implication, and on line 6 we have its left-hand side. So with an application of implication elimination, we get the right-hand side of the implication. Our goal is the right-hand side conjunct of the conjunction we have just obtained. And we can get it with an application of the appropriate rule for conjunction elimination. And then it remains to fill in some line numbers. To give you an overview, here's the derivation that we have just constructed. As you can see, there are no open assumptions and no holes in this derivation anymore. It is complete, and therefore we may conclude that the formula at the bottom is a tautology. In the next lecture, we will say more about why this is a justified conclusion. We have now presented the first example derivation involving rules for introduction and elimination of conjunction and implication. In the next lecture, we will discuss the notions of context and validity.
Okay. So let me just repeat. You have seen an example in which we have constructed a derivation proving that a certain formula, the formula you saw at the bottom of the derivation, is a tautology. And I hope you have recognized the strategy. So the example started with writing the goal and the formula of which we wanted to prove that it is a tautology at the bottom, in this case of the slide. And then the first thing we did was apply introduction rules to logically simplify the goal. And typically we applied the implication introduction rules. And with every application of an introduction rule, every application of an implication introduction rule, that is, we generated flags. And these flags contain assumptions that we can use when proving such implications. And they at some point cease to be valid. And the next video that will start after the break will be about that. And then after having generated a couple of those flags, we had to start looking at what we actually had and what kind of information we had generated during the application of the introduction rules. And for that, we used the elimination rules for conjunction and implication. Okay, so this is a very simple strategy, a very organized strategy also, that should help you construct derivations. So typically, especially at the beginning, giving derivations is quite straightforward if you understand the rules. And the rules are quite simple, I would say. So if you understand the rules, then it's a matter of just looking at which goal do I want to prove, and then which rule fits. And typically, until now, and for quite a bit, for quite some time actually, there will only be just one rule that fits. At least during this lecture, only at the end of the lecture, we're going to do an example where you actually have a choice. But and I urge you to adopt this style of working. Look at your goal. What is the main operator? What kind of connective is at the root, so to speak? Is it a conjunction? Is it an implication, and so on? And apply the associated rule, the introduction rule for that. Okay, I'd like to have a break now until what is it, 3:30. We'll reconvene at 3:30, and then we're going to go into more detail on well, what does such a derivation mean? Why is it correct? How do you deal with flags, and so on? So I'll see you back at 15:30. Also write this on my blackboard that I'll show you in a bit. I would say get a cup of coffee or a cup of tea, relax a bit so that you can concentrate on the second hour, which starts at 3:30. All right, ladies and gentlemen, welcome to this second hour of the lecture. As you may have noticed, I've written some of the questions, remarks that I saw in the chat, and also that were relayed to me by Peter Lamboy. I've put them on my blackboard here because they're actually good remarks and good questions. So maybe first I can address the comment that the lecture is going too fast, and I see what you mean. I already realized that myself when preparing for this lecture. I'm going to try to do something about that, but you have to realize that the videos that I'm using for this lecture have been recorded for another purpose. They have been recorded for the situation that you can watch them yourself at home at your own pace. So you can stop the video at any time that you need to. Of course, that is not possible in this stream, so that is sort of inconvenient. What I would like to say about that is, I hope to I understand you will not fully understand each individual video when you're watching it during the stream, but I hope that you get already an idea. And what I try to do after the video is pick out a couple of things that I want you to get from this first viewing of the video, so to speak. What you could also do, and that's for this I would like to take you a bit to the Canvas site actually. So here's the Canvas site. What I'm doing also, maybe you have noticed, is if you look at the syllabus, then you will find all the videos that appear in these streams. You find them on the syllabus. And some of the videos I don't show in the stream, and then I indicate this with this NIS, red NIS superscript. And well, I've already posted links to the videos for today a couple of days ago. I can try to do that as soon as possible, so that you have a chance, if you have some time, perhaps to have a look already before the lecture at the videos. I understand that this is maybe not the most convenient time for you to watch those videos. So I think it's also fine if you try to follow the stream. Except that not all videos will be crystal clear at the first viewing, but I'll pick out a couple of things that you need to get in this first instance, and then at home you can, or well, you are at home of course, but and then later you can rewatch each of those videos if you need to. For instance, when you're actually doing exercises. So let me go back to the board, because there was. Maybe it's good. No. Let me go back to the board, and so that is about the fact that the lecture is going too fast. I'll also do something about it by instead of showing a video of an example later on, I'm going to do the example on the board. So that should slow down the pace of the lecture also a bit, I hope. Which you can also do if there are things unclear. Don't hesitate to post your questions in the chat. This gives me an opportunity to actually give some further explanations, give some more details. For instance, using the blackboard that I have over here. So don't hesitate to ask for extra clarifications in the chat. A very good one that was actually posed in the chat is, why would you make a derivation instead of making a truth table? And that's actually an excellent question, because that's certainly the things that we could prove now with a derivation are exactly the same things as we could prove with a truth table. The point is, making the truth table, and especially when there are many proposition variables involved, may grow excessively large. So if you have 5 proposition variables, then you have 2 to the 5 possibilities, right, for the assignment. So you have a very long truth table, a very cumbersome truth table, and the longer the propositions get, the more cumbersome and, well, not very insightful the proofs get. So typically, then it is convenient to make to make a derivation instead, because it's much closer to the way we generally construct proofs. And also to the way a mathematician actually constructs a proof of a concrete statement. So I understand that for now it seems easier to actually construct a truth table, and perhaps it is that is actually the case for the propositions that we're going to prove that they are tautologies in this lecture. But as we go, and especially towards the end of the course, it will be making a truth table will not be possible anymore. And actually, that is definitely the case when we're going to start to prove statements about concrete things like sets and relations and functions. Then you cannot make truth tables anymore. So you have to bear with me for a bit, for 2 weeks, I would say, and then you'll get to see why this derivation system is actually much more convenient to give proofs than truth tables. So that's about why would you make a derivation. And then this last question actually is a nice bridge to actually the next video. So it's and also a very good question actually. So why does a complete derivation, I sort of reformulate the question a bit, but something to this extent was asked in the chat. Why does a complete derivation prove that the formula at the bottom is a tautology? That's an excellent question, and it will be answered in the next video that I'll start in a bit. This has to do with the fact that these rules sort of preserve a particular property. As you will, so basically these rules will establish logical consequence. And that is not something we are going to prove explicitly in this course, that you may take for granted that these rules are correct. But it's important to understand how this works. So let me now start the next video, and it's about notions such as context, validity, and why is a derivation correct in the sense that it proves the goal at the bottom.
In the previous lecture, we have presented introduction and elimination rules for conjunction and implication. In this lecture, we will present an example showing how to construct a derivation using these rules. We shall prove that the formula P implies Q and R implies P implies Q and P implies R is a tautology. A derivation always starts by writing the goal at the bottom. Then it is an advisable strategy to first try and apply introduction rules in order to logically simplify the goal as much as we can. The goal at hand is an implication, so to simplify it, we should apply the implication introduction rule. Of course, we do not yet know how long our derivation will be, so for now we leave out the references to the line numbers. The rule tells us to assume the left-hand side of the implication, here P implies Q and R, put it in a flag at the top of the derivation.
Apologies, guys. I realized that I started the wrong video. And that was also observed in the chat. Here we go again. Here's the right video. It's about context, validity, and correctness, I hope. I installed something incorrectly in my streaming software. But let's see whether this actually works.
In the previous two lectures, we have introduced derivation rules for conjunction and implication. And we have constructed an example derivation using these rules. In this lecture, we will discuss some important notions that you need to understand in order to construct correct derivations. And we will discuss why a derivation leads to the conclusion that some formula is a tautology. Look at the example derivation that we have constructed in the previous lecture. We distinguish two types of formulas in this derivation. We have assumptions and we have conclusions. We will focus on the assumptions first. They're easily recognized because they are put in a flag. And the flagpole indicates the scope of the assumption. For instance, the scope of the assumption on line 1 ends when the rule that generated this assumption is applied. So the scope of the assumption on line 1 ends just before line 11. It's very important, the notion of scope is very important because it determines at which places you may still use an assumption in a derivation. And to make this a bit more precise, we introduce the notion of context. The context of a certain line in a derivation is the conjunction of all assumptions that have this line in their scope. And we adopt the convention that true, the abstract proposition true, will denote the empty conjunction, or in other words, the empty context. Let's illustrate the notion of context considering the example derivation you see over here. On the first line of the derivation, the assumption P implies Q and R is stated, and its context, therefore, is this formula. On line 2, the assumption P is added to the context. The context of line 2, thus, is the conjunction of the formulas on lines 1 and 2. The context then remains unchanged until the scope of one of the assumptions in the context ends. With the implication introduction before line 5, the scope of the assumption of line 2 ends, and therefore the conjunct P is removed from the context. On line 6, the assumption P is added again, and the context remains unchanged for the next couple of lines. When the scope of the assumption on line 6 ends, the conjunct P is removed again from the context. And when the scope of the assumption on line 1 also ends, we are left with the empty conjunction, which is true by convention. Assumptions should not be used outside their scope. For instance, the assumption on line 2, P, can only be used on lines 3 and 4, but it should not be used after line 5. We make this idea precise using the notion of validity. A formula at some line in a derivation is valid on this line and all lines below it, but until the scope of one of the assumptions in its context ends. Let's illustrate also this idea on our example. The assumption on line 1 is valid until its scope ends, with the application of implication introduction just before line 11. In other words, it is valid on lines 1 to 10. The scope of the assumption on line 2 ends with the application of implication introduction just before line 5, and hence it is valid on lines 2 to 4. The formulas on lines 3 and 4 are valid until the scope of the assumption on line 2, which is in their context, ends. Note that the context of line 5 consists of the assumption on line 1 only, and hence the formula on line 5 is valid until the scope of the assumption on line 1 ends, which is just before line 11. The assumption on line 6 is valid until its scope ends just before line 9, and the formulas on lines 7 and 8 are also valid until then. The context of lines 9 and 10 again consists of the assumption on line 1 only, of which the scope runs until just before line 11. Since the context of line 11 is empty, the formula at line 11 will never lose its validity. It is valid forever. The reason why the notion of validity is so important is because the correctness of the rules we have presented so far and the correctness of the rules that we will present later depends on it. Rules may only be applied to formulas that are valid, and this is called the validity condition. Let's check on our example whether the validity condition is satisfied. The application of the implication elimination rule to conclude the formula on line 3 uses the formulas on lines 1 and 2, which are both valid. The application of the conjunction elimination rule to conclude the formula on line 4 uses the formula on line 3, which is valid. Then the application of implication introduction to conclude the formula on line 5 is based on the idea that the right-hand side of the implication can be derived if the left-hand side is added to the context. In a way, the formula on line 5 is a conclusion from an entire subderivation, which starts with the assumption of the left-hand side on line 2 and ends with the conclusion of the right-hand side at line 4. The formulas on line 2 and 4 are indeed valid when the implication introduction rule is applied, but as a side effect, their validity does end with this application, and therefore we depict the situation a bit differently from the previous rule applications. The rest of the analysis is unsurprising. The implication elimination leading to the conclusion on line 7 uses the valid formulas from lines 1 and 6. The conjunction elimination leading to the conclusion on line 8 uses the valid formula on line 7. The application of implication introduction leading to the conclusion on line 9 uses the assumption on line 6 and the conclusion on line 8. Both are valid, but their validity ends with the application of the rule. The application of the conjunction introduction rule leading to the conclusion on line 10 uses the valid formulas on lines 5 and 9. And finally, the application of the implication introduction rule leading to the conclusion on line 11 uses the assumption on line 1 and the conclusion on line 10. And as a side effect, the validity of all formulas from line 1 until line 10 ends with the application. We are now in a position to justify our conclusion that the formula at the bottom of this derivation is a tautology. A crucial observation is that every application of a derivation rule introduced so far establishes that its conclusion is a logical consequence of either the conjunction of its premises or directly of its context. Let's check this for a few cases on our example derivation. Consider the application of implication elimination leading to the conclusion on line 3. The formula Q and R on line 3 is a logical consequence of the conjunction of its premises, the formulas on lines 1 and 2. As an instructive exercise, you may want to verify this by checking with a truth table that whenever the left-hand side formula evaluates to true, then so does the right-hand side formula. Considering the application of conjunction elimination leading to the formula on line 4, indeed, the Q is a logical consequence of the conjunction Q and R. In fact, we have presented this earlier as a standard weakening. Next, consider the application of implication introduction leading to the conclusion on line 5. From the reasoning on lines 2 to 4, it may be concluded that Q is a logical consequence of P implies Q and R, extended with the conjunct P. Then, indeed, it follows that the formula P implies Q is a logical consequence of P implies Q and R alone. The application of conjunction introduction leading to the conclusion on line 10 gives rise to a trivial weakening. And finally, the application of implication introduction leading to the conclusion on line 11 gives rise to the conclusion that the considered formula is a logical consequence from an empty context. Of course, that this last weakening holds is not so easy to see. In fact, the point of constructing the derivation in the first place was to prove this fact. Of course, we should officially provide a formal argument that all of our rules satisfy the property that they establish a logical consequence. We shall not do that here. It is outside the scope of this course. What you should remember is that if a derivation is complete and it's constructed correctly according to the rules, observing the validity condition, which says that you can only apply a rule to formulas that are valid in that particular place in a derivation, then every formula is a logical consequence of its context. Well, if P is a logical consequence of the context denoted by true, the empty context, then P is a tautology. And therefore, we can now safely say that the conclusion that the formula at the bottom of this derivation is a tautology is justified. In this lecture, we have discussed the important notions of context and validity, which you need to understand to be able to construct correct derivations. We've also provided some justification for the conclusion that the formula at the bottom of a complete derivation is a tautology. In the next lectures, we will introduce more rules to deal with other connectives and to deal with quantifiers, and we shall give more examples of derivations.
Ladies and gentlemen, that was a video in which it was explained why a derivation actually proves that the formula at the bottom is a tautology. What you see here is again the derivation, and there was a question that I'd like to answer by looking at this derivation, a question about the assumption P that you, as you may notice, actually appears twice in this derivation. So here P is assumed and here P is assumed. And the question is it necessary to assume this P twice? And the answer is yes, that is necessary because look what happens, and this is something that was explained in the video actually. So here we are trying to prove, so this part of the derivation proves actually P implies Q. Right? And how do you prove an implication? Well, you apply the implication introduction rule, which kind of generates this assumption, and then the goal was to prove this Q. Now, the idea is that this P, the validity of this P, ends when you do the implication introduction. So there are two points that you should understand here. First of all, this flag in which we see the P. It's not something that's sort of that was just invented just like that or inserted just like that in the derivation. It is inserted for a reason. It is actually caused by the implication introduction rule. This is always an advice, I always urge you to only stick to applications of rules and never start to raise flags just like that. The flag comes from the implication introduction rule. Now, if you do that, then actually the flagpole here will end with the implication introduction rule, and so this P is no longer valid in this part of the derivation, right? So we need it again. We need it again to prove P implies Q. P implies R over here. So that's about the assumption being stated twice. It's basically the effect of applying the rules, and that's what you should do. So it's something that you should not worry about, and actually will be necessary. And another question that I see coming now, and I'm very pleased to see that there are now that you're starting to ask questions via the chat. Does P implies Q become part of the context after line 5? Officially, it's not part of the context. So the context is simply made up of all the assumptions that are still open. So say at line 6 or 7 or 8, so at line 6, there are two assumptions open, namely P implies Q and R and P. So these two formulas constitute the context. But P implies Q has been proved over here. So it is valid until one of the flagpoles that is still open closes. So this formula will remain valid, and valid means you can still use it in your derivation until this point over here. Okay, so that's about validity. So P implies Q is not part of the context. The context is made up of assumptions only, but it is valid, and it is valid until the flagpole ends over here. There was another question. On page 64 of the book, the following is stated: false is stronger than P. Let me move to the blackboard to actually to be able to. That's not where my blackboard is. Where's my blackboard? First, I have to get my mouse. There is the blackboard. So the question is: P. We have false is stronger than P, and P is stronger than true. That's both the case. How is it possible that on the slides in the video just now we have true is stronger than P? So let's separate these two things. What happens here is these two statements are always true. Yeah, these are always valid. So P is always a logical consequence of false. True is a logical consequence of every abstract proposition. Now here is in the video, at some point it was concluded that true is stronger than P, but this is only the case when P is a tautology, or and this was what was the case in the video when actually we have shown that P is at the bottom of a complete derivation. And complete here means that we don't have open assumptions. There are no flagpoles that we should still pending, basically, that we should still close, right? And that was the case in the video. So this statement, the statement true, P is a logical consequence of true, is only the case when P is a tautology. And that was basically the argument that was put forward in the video. You may want to watch it again later. And now another question is, how can we say that true is the stronger equivalent if we know true as the weakest proposition of all? Well, that I think it's the same question actually. So again, we have this logical consequence only in very specific cases that this P actually is a tautology. So basically, referring back to, let me show you again the slides here. referring back to actually what you saw over here. So what is the situation? We have this long formula here at the end of the derivation. And as you may notice, this is a complete derivation. There are no holes anymore in this derivation. And moreover, the context is empty because, well, this assumption was still open until we did the implication introduction. So that means, and the invariant that is maintained is that the formulas that you see at successive lines in a derivation are logical consequences of their context. Now, the context at this point, at line 11, is empty, because we have basically withdrawn the last assumption that was still open. So we have an empty context, and the empty context corresponds to true, right? It's the empty conjunction of a number of assumptions, and so the empty conjunction is true. And so in this case, we do have basically we can conclude that this formula here is a logical consequence of true. And because we also know that true is a logical consequence of P, we know that P is actually equivalent to true and therefore a tautology. That's the reasoning that is going on here. Okay, hope this clears up those questions. There was still one more question that was asked some time ago, and that was about more an organizational matter, I would say. So the question was, do we have to know the rules by heart? Well, I'm paraphrasing here. I think the question was formulated a bit differently. But the answer is yes, you should know these rules by heart. You should practice with them a lot, and I'm sure that after you have done 20 implication introductions, you know how implication introduction goes. And moreover, these when you get used to these rules, they're very natural. They're actually called, they are sometimes referred to as natural deduction style rules, because they're very close to the kind of reasoning that we do in everyday life. Maybe you don't realize it yet, but that's what you actually do. All right. That's about context and validity. I don't see any more questions appear in the chat at the moment. What I want to do next is I'm going to show you one more set of rules, rules for negation. Well, actually, one rule we are going to introduce introduction and elimination rules for negation, and after that, I'm going to actually show you an example on the blackboard. So please watch this video for a bit, it's not very long, and then we're going to do an actual derivation on the board.
In this lecture, we shall discuss how to deal with negations and contradictions in a derivation. First, we shall present introduction and elimination rules for negation, and then we shall discuss the important proof by contradiction method. Let's start by considering negation. The negation not P is true if and only if P is false. So this suggests that to prove that a negation is true, it is enough to prove that the negated formula is false. However, our proof system, our system of derivation, is not really designed to prove that formulas are false. This has to do with the invariant that we would like to maintain, that every formula is a logical consequence of its context. So we need another method. Instead, the trick is to insert the formula that is negated, the P in this case, in the context, so stated as an assumption, and to try to derive a contradiction. If we manage to do that, then we may also conclude that the negation is true because the negated formula P is inconsistent with the context. To prove the negation not P, assume P and try to derive a contradiction. For if this succeeds, then by an application of negation introduction on m and n-1, not P follows. As indicated by the arrow, in the construction of a derivation, this rule is used from bottom to top, and it replaces the goal not P by the simplified goal to derive a contradiction. The introduction rule for negation requires us to prove a contradiction. Now the question arises how to prove contradictions in a derivation. Note that if both P and not P are valid in a certain context, then we have a contradiction in disguise, because from P and not P, a contradiction is a logical consequence. So this gives rise to the following principle. From a formula and its negation, we may conclude a contradiction. Let's put this in the form of a derivation rule. If both not P and P are valid at a certain place in a derivation, then a contradiction may be concluded using the negation elimination rule.
All right, guys, that stopped quite abruptly, I can imagine. So I was not aware of that the video was already stopped. You know, I'm starting these videos, and I can only see I can only see the image and not I don't hear the sound. So in this case, because there was no clear end, I didn't notice actually that it was finished. All right. What I'm going to do now, let me first show you this slide over here. So what I'm going to do, I'm going to use, and I'm going to do what I would normally do in a lecture, in a lecture hall. I'm going to show that some formula here, P implies not Q implies not P, is a tautology, and I'm going to use the system of derivation that we have seen until now, and the rules that we've seen so far. All right. So what I'll do now is I'll go to my blackboard. You see these very tiny images in the right hand side, top right. I'll get to that. I'll show you what they're for. You can ignore them for now. The first thing I need to do, and a derivation always starts like this, is to write the formula that I want to prove is a tautology at the bottom. So I'm writing P implies not Q implies Q implies not P at the bottom of my sheet, or whatever I'm using, in this case my iPad. And now basically I'm going to analyze what I have over here. I see that the formula that I have to prove has the shape of an implication. Right? The implication is the main symbol. Basically, I should ignore what is really inside the left-hand side of the implication and the right-hand side implication. I should focus on the implication. I want to prove an implication, so I should now think, well, what should I do if I want to prove an implication? Well, for that, and this is why I have these things over here. For that, I should look at the rules that I have at my disposal, and there's actually only one rule that I can sensibly apply, and that is the rule for implication introduction. Right, that is this rule. It says that if I want to prove an implication, I should assume the left-hand side of the implication. That is the P in the rule. In this case, it will be the left-hand side of the implication, and the remaining goal is then to prove that the right-hand side of the or then I should produce a derivation of the right-hand side of the implication. So that's what I need to do. Let me make this smaller again. I might need it later. That's what I'm going to do here. So I'm going to do implication introduction, and I don't know yet. Well, I'm sure that the assumption will appear on line 1 of my proof. I don't know yet at what line the goal will appear. So I leave that open for now. I need to establish now that Q implies not P. Okay, and I want to do that assuming the left-hand side of the implication. And as you can see over here, the left-hand side is P implies not Q. So I put that in a flag. And note, I don't invent the flag myself. The flag is produced by an application of the rule. I apply the implication introduction rule, and this gives me the flag P implies not Q. That is my assumption. There you are. And the nice thing about iPads is that actually this can become a straight line. Okay, so now now I basically repeat what I just did. I analyze what I should prove. I analyze my goal, and I notice that again I have an implication. So I can apply the same rule to simplify this new goal. I do implication introduction again. And I'm sure that my assumption will appear on line 2, but I don't know yet what will be the line number of at which I will place the new goal. The new goal will be not P, so this is line. By the way, this is line 1. And now I assume the left-hand side of the implication, which is Q. And that is on line 2. And now my new goal will be to derive not P. And I should derive not P in the context that I have now created, basically by the applications of the implication introduction rule. So my context consists of P implies not Q and Q. But let's not worry too much about the context yet, because we have another simplification step to do actually here. We have a negation, and so we should apply a rule for one of the rules for negation. Well, there's actually only one rule that we can sensibly apply, and that is the rule for negation introduction. That is this rule. And negation introduction says that if we want to prove not P, the negation of some formula P, then what we should do is we should assume P and derive a contradiction. Yeah, so that's what we're going to do. We're going to assume P and we're going to derive a contradiction. And that again will generate an extra assumption. So my context grows, and that's convenient because that gives me more information to actually establish the goal that I want to achieve, the goal that I want to prove. So so I get another assumption. This will be on line 3. And the assumption will read P. And now I need to prove, I'm starting to write a bit smaller because otherwise it's not going to fit. So I do negation intro on 3 and, well, actually what do we have here? And that's now the goal is now to prove false, to derive a contradiction. Now the question is, and now false, well, we do have a false introduction rule. I'll comment on that a bit later. It did not appear in the video because it's something you will actually never use. What we should now see, let me get this straight. So what we should now realize is that, okay, to prove false, what you basically want to do is get a contradiction out of your context, right? So we have to combine the statements that we have, the formulas that we have in our context. So P implies not Q, Q and P. We somehow have to combine them to find the contradiction. Now, here's how we can do that. I mean, we don't have a rule to combine, say, Q and P. We don't have a rule to actually combine P implies not Q and Q. But what we do have is a rule that actually says, well, if you have an implication, P implies not Q, and it's left-hand side, then you may eliminate the implication. Let me show you also this rule. That was part of the rules for implication. It's actually an implication elimination rule. Here you have it, right? If we have an implication, P implies Q, and we have the left-hand side of the implication, then we can conclude the right-hand side of the implication. Okay, so that is what we're doing next. So there we go. We have the implication, which is P implies not Q, and we have the left-hand side of the implication. So we conclude by implication elimination, and we do that on 1 and 3. We get the right-hand side of the implication, which is actually the formula not Q. Right, so note we have the implication, it's left-hand side, it's over there, and therefore we can conclude not Q. And now there's one more step we need to do. We need to realize that actually we have Q and we have not Q, and both are valid in this context, right? So we can combine these two. These formulas are still valid over here, so we can combine them using the rule for negation elimination. Let me show you that one just before we apply it. So we have the rule for negation elimination, which says that if we have not P and P, so the negation of something and this something, then we can conclude a contradiction. And that's exactly what we want to conclude. All right, so let me reduce this again. So there we go. We can now apply negation elimination and basically finish the proof. So now this is, by the way, line 4. I could have written that already. So we do negation elimination on lines 2 and 4. And this indeed closes the last gap that we still had in our derivation. Right, so we now may genuinely conclude false here. It's a valid conclusion now, so that will appear on line 5. I can now finish the derivation by filling out some line numbers. This will be line 6, and this is line 7, and there you are. This is line 8. And now in 8 steps, in 8 derivation steps, we constructing, well, basically starting at the bottom of the writing the formula we wanted to prove at the bottom, applying elimination introduction rules to simplify the goal until we have the simplest goal possible. That's this one, and then using what is in the context to actually prove that goal. That is how we have proceeded to actually construct this proof. I see a question in the chat. Actually, the question is there some kind of explanation on why these rules work? Do we need to understand them? Well, the explanation. Let me show my face again in this, so that you can actually see who's talking to you. The explanation is in part actually in the video. You could say that we have shown just now. What now remains is to show for each and every individual rule that indeed it satisfies or preserves this property that if you conclude a certain formula, it is actually a logical consequence of its context. And you can, and we are not going to discuss this in detail in this course. The book spends some words on it. It provides some explanations as to why the rules are correct, but it relates it to some other formal system, the system of calculation that we have not discussed in this course. I suggest that you think a bit about it. I try to motivate it also by referring to truth tables in the respective videos that discuss the rules. And then there's the question about false intro, question whether you can also use that. Well, that is a nice bridge actually to some slides that I still have here. Let me move to these slides, and then I'll show them to you. So let me start. Just a sec. Let me start here. There you go. So here you see the rules that we have seen for negation. So to prove a negation, this is a rule that we have just applied, right? You assume P and to derive a contradiction, and this is the way to prove not P. And similarly, if you want to prove false or establish false in a reasoning, sorry, I should maybe have shown also this rule. So how do you use a negation in a reasoning? Well, if you have the negation of some formula and you have the formula, so you have not P and you have P, then you can conclude a contradiction, false. Now, this rule false introduction, it's also mentioned in the book basically for completeness. It looks very much the same, and it's basically based on the same principle. So if you have P and not P, a contradiction, then this will be actually stronger than false, simply because it is equivalent to false, right? And this is the motivation also for the rule that says, well, if you want to prove false, then how could you proceed? Well, you could actually try to prove not P and P. The question only is here, which P? Right. So, and this is the reason why false introduction. It's really similar, or actually, it's similar to negation elimination. The difference is, if you do negation elimination, you basically have you see in your derivation, hey, I have established not P and I have established P. Okay, then I can conclude a contradiction. That is the way you apply negation elimination. It's basically when you're reasoning from top to bottom. When you're actually into forward reasoning, as I call this in the videos. The rule for false introduction officially is a bit different. It's basically starts from the assumption that you want to prove false, and then somehow are going to do that by trying to prove P and not P. The problem here is, what is the P that you could use? typically this has to come from the context. And therefore, usually we're not going to apply false introduction, but rather negation elimination. But now to the question, so could you use false introduction? Well, it is okay, but actually what it's fine if you mention it, if you make a derivation and you call this step false introduction, that is always correct. But actually in the way you construct it, strictly speaking, it was negation elimination. So I said that's why I don't discuss this rule in the video. You never need it, basically, this false introduction. So it is strictly speaking a rule that you would apply when this is your goal. All right. So to summarize, this false introduction is essentially the same as negation elimination. After you have completed your derivation, you will not see the difference between the applications of these rules, except for maybe the fact that you mention at some place false introduction rather than negation elimination. But otherwise, there's no difference at all, and so you actually don't need this false introduction rule. But it is there for completeness in the book. The subtle difference, which you don't see in a completed derivation, but which somehow you do see when you're constructing a derivation, is that false introduction is actually intended for reasoning from bottom to top, whereas negation elimination is intended for reasoning from top to bottom. So my advice to you, although it is always fine to apply a false introduction, my advice to you is to just learn by heart negation elimination. This is the rule that you actually need, and not false introduction. I want to show you one more rule before we have another break, and that is also a rule that is not discussed in the video, and that is actually a bit of an omission. I should still make a video about the elimination of false. So I'm presenting it here to you in slides. It's also explained in the book, but it's not mentioned in the video. The idea is this. If somehow at some point in your derivation you have proved false, then, because false is the strongest proposition of all, everything is a logical consequence of false. As you may have noticed when we discussed logical consequence, actually we have the following rule, which is a bit surprising at first. If you have established false somewhere in the reasoning, then you may always conclude anything you like at that place. But note, this is always in a particular context. So there will be assumptions open still. There will be flagpoles that have not yet ended, and you need to end them. So you will never manage to prove, and the rules are such that you will never manage to prove false without any still pending open assumptions, and therefore, you should not. You should realize that this doesn't come for free, so to speak. So, but if you're in a lucky situation that you actually have concluded false somewhere in your derivation because you somehow have a contradiction, then you may conclude anything you like, and that can be very convenient. All right. That is still what I wanted to say about negation and false. This is the derivation that we have already done. I propose that we have a break now and we reconvene at 16:30, so at 4:30. And in the meantime, I'd be happy to see your questions in the chat so that we can address them after the break. We continue with the lecture at 16:30. Okay, ladies and gentlemen, maybe just a couple of things that I noted in the chat. So there was a question of which I'm not sure what was meant there, but there was a question about, I think, equivalence and logical consequence. Maybe it helps to realize that that we have this statement over here. So if you know that that Q is a logical consequence of P, and P is a logical consequence of Q, then it follows that P and Q are equivalent. And this is a fact that is used in the video. And maybe the question was about that. The other way around is also the case. So if you know that P is equivalent to Q, then we also have that that Q is a logical consequence of P and vice versa. All right. So there's an if and only if there. So, but you need to have both to be able to conclude the equivalence. Another question that I noticed in the chat is this one: can you use flag-style derivations to prove that a formula is a contingency or a contradiction? And the answer is no. Well, that is for proving a contingency is sort of complicated. Proving a contradiction, that's also not what the system is designed for. It's really designed for proving that propositions are tautologies, or that mathematical statements are universally true. That is not to say that you could not actually use the system to prove that some formula is a contradiction, but what you do is prove, if you for a contradiction, what you can do is prove that its negation is a tautology, right? Because if some formula P is a contradiction, so a formula P is a contradiction if its negation is a tautology, and then you could use the flag-style derivation to prove that the negation of the formula is actually a tautology to conclude that it's a contradiction. But this is not what we are going to use flag-style derivations for. We're going to use it to prove as long as we're talking about pure logic, like propositional logic and predicate logic, then we're going to just establish that some formula is a tautology. Later on, we're actually going to use the system also to give proofs of mathematical statements. All right, and then this question, it came up already before. Let me stress the answer to that. So, do you need to know the rules by heart? And the answer is yes. So you need to learn these rules. I cannot stress this enough. Already for the next test, you need to know the rules that are relevant for that test, and those are the rules that are really about propositional logic. You learn these rules best by practicing a lot, by doing exercises. So don't try to try to learn these rules by heart by looking at them for a long time or something like that. Try to apply them, because by applying them you learn them better. Okay. Ladies and gentlemen, we're now going to continue in this last hour with two more basically stretches of rules. First, we are going to discuss the notion of proof by contradiction. I have a video that explains it. Actually, it's the second part of a video that you've already seen. The second part of the video that discusses negation. So I'll show that first, and then I'll come back for a bit, and then we start an example of a proof by contradiction. I'll also show this by a video. Let me also stress again that I realize that these videos are recorded in such a way that you sometimes need to stop them to study, to think about what is being said, and of course you don't have the opportunity in the stream to stop the video. So I suggest that you take for granted that maybe not everything is completely clear, so that you can return to it later on after the lecture and again have a look, watch the video. It's a very good strategy, I think, to watch a video right before you are starting to make exercises. The videos are posted on the syllabus on Canvas on the syllabus page, so you'll always have access to these videos right away. Okay, let me start the video that explains proof by contradiction. It starts kind of right away because it's the second part of a video that we've already started. There we go. We proceed to discuss a powerful proof technique that is called proof by contradiction.
Before we formulate this as a general rule, let's first consider an example from mathematics. Let's try to prove the statement for all integers x, if x squared is odd, then so is x. First of all, we observe that we need to prove a universally quantified implication. So we declare an arbitrary integer x and suppose that its square is odd. Now our new goal is to prove that then also x itself is odd. Note that for this we need to show that x is a multiple of 2 plus 1. From the assumption that the square of x is odd, it follows that there exists y such that the square of x is 2 times y plus 1. Hence, we can write x as the square root of 2 times y plus 1. And now we run into a difficulty. For this expression for x as the square root of a multiple of 2 plus 1 does not give us a clue on how to write x itself as a multiple of 2 plus 1. We need to find an integer z such that x is equal to 2 times z plus 1, but it is not clear how to derive the existence of such a z from the derived fact that x is equal to the square root of 2 times y plus 1. The thing is that from such an expression for x, it is fairly straightforward to derive a similar expression for x squared, as we have done before, but the other way around is not so straightforward. Let's start over with our proof, but now use a slightly different approach. We need to prove that x is odd, but in order to do so, we suppose that it is not odd, and argue towards a contradiction. If we manage to derive that x is not odd indeed leads to a contradiction, then we have established that it is inconsistent with the assumptions generated by the universally quantified implication. The conclusion that x must be odd is then justified. Now let's finish the proof. Clearly, if x is not odd, then it's even. So there exists an integer y such that x is equal to 2 times y. Then we can do a similar computation as we have done in an earlier lecture. We find that the square of x is 2 times 2y squared, and 2y squared is an integer. So we get that the square of x is even, and this is in contradiction with the assumption that the square of x is odd. To summarize the general idea, in order to establish our goal, we have assumed its negation and derived a contradiction. This is enough as a proof of the original goal. Let's formulate the principle of proof by contradiction as a general derivation rule. It is a proof principle that serves to establish some general goal P at line n in some derivation. It states that it is enough to derive a contradiction from the negation of the goal, to conclude that the goal is true. The Latin phrase reductio ad absurdum is often used to refer to the principle of proof by contradiction, so we shall use the abbreviation RAA to refer to this rule. You may have already observed a similarity between the principle of proof by contradiction and negation introduction. It is instructive to consider this similarity in a little bit more detail, so here we go. Here you see the rule for negation introduction. We may instantiate it by replacing the P in the rule by not P. We then get approximately the reductio ad absurdum rule, except that it leads to not P rather than P. To get P, it remains to get rid of the double negation. Applying negation twice yields an equivalent formula. As you can see from the truth table over here, the column for not P is identical to the column for P. So, P is a logical consequence of not P, and this gives rise to the following proof principle. From the double negation of some formula, we may conclude the formula itself. Let's formulate this as a derivation rule. If the formula not P is valid at some place in our derivation, then we may conclude P with an application of double negation elimination. Now we can derive the rule for reductio ad absurdum using the rules for negation introduction and double negation elimination. To prove P, first note that not P can be established using a normal application of negation introduction. It amounts to assuming not P and deriving a contradiction. Then, from not P we can conclude P with an application of double negation elimination. Thus, we have achieved the same effect as with the proof by contradiction method. The reductio ad absurdum rule is a rule that applies from bottom to top. And as you may notice, it doesn't put any requirements on the goal you need to establish. It's always applicable. And we need to issue a warning here, because it is a powerful proof technique because it's always applicable, but it's also a dangerous proof technique because of this. In some cases, application of this rule does not lead you closer to completing your derivation. So we have now seen three types of rules. We have seen introduction rules, which allow us to logically simplify goals. We have seen elimination rules that allow us to infer conclusions from valid formulas in a derivation. And we have now seen a third type of rule. It's called proof by contradiction. And my advice with this rule is to apply it only when the other two types of rules are no longer applicable. This concludes our discussion of introduction and elimination rules for negation and of the proof by contradiction method. The next two lectures will be devoted to constructing examples using these new rules. The first lecture will discuss an example involving only the introduction and elimination rules for negation, and the second example will involve a proof by contradiction.
Okay, ladies and gentlemen, let's have a look at the most important message of the part of the video that you have just seen. So it started with a motivation as to why sometimes you need a different method to prove a mathematical statement, say P. Sometimes it's not so. I mean, if you have a certain statement that you want to prove, it's not so easy to follow the direct proof method. So sometimes it is necessary to actually assume the negation of P. So assume that P is not true, and then derive a contradiction. Now, this is a very dangerous rule, as I will explain in a bit, but here you see it. So the idea is that if you want to prove a formula P, then you could proceed as follows, and the rule is called reductio ad absurdum in the video. So you could assume that P does not hold, so you assume not P, so you put a negation in front of the formula that you want to prove, and then try to derive from the negation of the formula a contradiction. That's the main message of the part of the video that you have just seen. This is a proof method that you can sometimes use. I should point out to you that the name reductio ad absurdum, it's a Latin phrase that is sometimes used for this proof method. In the book you'll find different names. You'll find proof by contradiction, and you'll also find, and it also explains a sort of detour where you apply the rules for double negation and for negation, as is also, by the way, explained in the video. What you may use either name. You may either write RAA, or you may write proof by contradiction, or you may use the more elaborate method that uses double negation, rules for double negation and negation. Why is this a dangerous rule? Well, so far, when we're using rules from bottom to top, we are looking at the formula at the bottom of our goal, basically to prove, and then we looked for a rule that fits. Right, so if we had an implication, what we are going to do is implication introduction, and there was only one rule to do that. Or if we had a conjunction, then there was basically one rule that explains, well, if you want to prove a conjunction, this is what you do. Now the difference with the rule that you see over here is that it has an arbitrary formula as a goal. It doesn't require any logical structure. It doesn't have to be an implication or a negation or a conjunction. It can be anything. And this makes it very dangerous, because it means that the rule is always applicable. It's always applicable, but it does not always lead to good results, in the sense that you may think of it as a simplification, but it's not always easy to actually prove this contradiction from the negation of the formula, and there's often a more direct method to do so. So you should really treat this rule with care. You should only apply it when basically you're in a situation that you don't know how to apply something else, or your goal is very simple. It's typically a proposition letter, and in the context you don't see how you get this goal from the context. If that situation arises, then you may give it a try with an application of this rule, but use it with care. That's what I want to stress. All right, sometimes it is necessary to apply this rule, and in the next video you'll see an example application. So I'll start the next video and then you'll see an application of the proof by contradiction method.
In this lecture we shall give an example of a derivation that uses the proof by contradiction method. We shall prove that the formula not P implies P and Q implies P is a tautology. As always, when constructing a derivation, we start by writing the goal at the bottom. The main connective of the formula to be proved is an implication, so we apply the rule for implication introduction. According to the rule, the left-hand side of the implication is added to the context in the form of an assumption, it's put in a flag, and the right-hand side of the implication becomes the new goal of the derivation. The new goal is the abstract proposition denoted by P, which does not have any logical structure exposed. We should at this point consider whether we can perhaps derive it from the context. The context at this stage consists of the implication on line 1 only. Note that from the right-hand side of the implication we could derive P by conjunction elimination. To get the formula P and Q, we would then like to apply implication elimination. And for the application of that rule, we should have the left-hand side of the implication. We therefore insert it as a goal. Indeed, supposing for the moment that we can derive not P, then we can apply the implication elimination rule, for we have the implication on line 1 and its left-hand side not P. So with an application of implication elimination, we can then infer the right-hand side P and Q of the implication. We now want to derive the left-hand side conjunct of P and Q. The rule for conjunction elimination allows us to do so. Our proof is not finished. There is still the goal not P that should be established, and this will turn out to be problematic. We might still apply the negation introduction rule, which would add P to the context and makes false the new goal. But then we are sort of stuck. From a context consisting of the formula on line 1 and an additional P, we cannot derive anything. At this point, we realize that our attempt to get a complete derivation of P by inserting the new goal not P failed. We should look for an alternative way. So let us now backtrack and resort to a proof by contradiction, as formalized by the RAA rule. The RAA rule states that in order to derive some formula P, we may assume the negation of P and derive a contradiction. The new goal is to derive a contradiction represented by the abstract proposition false. There is no clear-cut method to establish this goal from first principles, so we now switch to forward reasoning mode. Let's consider again the implication on line 1 and try to apply the implication elimination rule. Thanks to the application of the proof by contradiction method, we now have the left-hand side not P of the implication on line 1 in the context. So we can now apply the rule without inserting extra goals, and we get the conjunction P and Q. On the conjunction, we can apply the conjunction elimination rule to get the left conjunct P. Then, both not P and P are valid. So with an application of the negation elimination rule, we get the contradiction we were after. Our derivation is now complete. It does not have any gaps. So we may conclude that the formula at the bottom is a tautology, as we set out to prove. This concludes our construction of an example derivation that involves proof by contradiction.
All right, guys, this may be time for a small distraction after this difficult proof by contradiction. I suggest that you watch that proof again. I want to discuss a couple of more rules in a bit, but let's first do some real logical reasoning. And this is about a lion that lives in the so-called forest of forgetfulness. And this lion is a strange being, because what does he do? He lies every Monday, Tuesday and Wednesday. and on all other days of the week he will speak the truth. Okay, so lion lies every Monday, Tuesday, and Wednesday. Every other day of the week he speaks the truth. Now, what about this lion? On which days of the week, and this is the question that I'm asking to you, and I'm going to do a small quiz in Mentimeter. On which days of the week could the lion make the following two statements? I lied yesterday, on one hand. The second statement is, I will lie again 2 days after tomorrow. Now, just to get you maybe thinking a bit, maybe you got worn out by seeing so many videos and so many rules. Let's do some logical reasoning. You can go to Mentimeter. Let me also show you the poll here. You can go to 9298428 at menti.com and cast your statement. I'll put back the slide in a bit. So if you have the Mentimeter code, I think I have it on slide actually. Yeah, there it is. Right, so I suggest you cast your answers. I give you some time to think about it, say 2 minutes, 3 minutes, and then we reconvene. All right, let us see first what is the result of the poll, and then then we'll explain. Let me switch here. So let's see what you have answered. All right, So the vast majority, well, the vast majority is not actually true. 34% of you say Monday. I see all sorts of votes for all other days too. Thursday is quite popular. So let's do a bit of reasoning here. Let's go back to the slides and see what actually is going on here. So this lion is lying on Mondays, Tuesdays, and Wednesdays, and on all other days he speaks the truth. So now, if the lion says, "I lied yesterday," then either basically if he speaks the truth, right? So if he says this on a day that he speaks the truth, then it can only be Monday, because on Monday, indeed, the day before Monday, actually Sunday, he is lying. Right, so the other day that is still possible here is Thursday, because on Thursdays he lies. So if he says on Thursdays, "I lied yesterday," then indeed he's lying because he speaks the truth on Wednesdays. All right, so basically the first statement excludes all other days except Mondays and Thursdays. Now, I will lie again 2 days after tomorrow. We can now investigate again whether Monday or Thursday are possible. So I will lie again 2 days after tomorrow. So if it would be Thursday, then 2 days after tomorrow, Thursday is Friday is Saturday. Then he cannot, I mean, then it has to be, so if he says this on Thursday, then it should be a lie, right? So then actually he should speak the truth 2 days after tomorrow, and that's not the case, because on Saturday still this lion lies. So basically the second statement excludes Thursday. So the answer is, should here be Monday. All right, that's for a short intermezzo. Now I hope you're ready for a last stretch of logic and set theory. Instead of giving you a video, what I've decided to do is, let me first get rid of these slides, because otherwise you cannot see anything like this. Instead what I will do is I'll show you a couple of rules. I'll quickly discuss them and spend some time on actually on an example applying these rules, and probably I'll not finish the example. There are 2 videos actually that you can watch, both discussing the rules and also discussing the example. So don't worry if we don't manage to finish it. There's a video that explains it in detail. All right, so we still need rules for disjunction. And well, there are basically 2 rules that we're going to use. So first, let's discuss disjunction elimination. If we know that some disjunction P or Q is true, then well, from the disjunction itself, we cannot yet conclude anything directly. But if we also know, in addition, that not P is true, then, well, we know that P or Q must be true, and if we know that not P is true, then actually the P cannot be the one of the two. It cannot be the one that is true, so it must be Q actually that is true, right? So from P or Q and not P, we may conclude Q. That's for disjunction elimination, and then we have a similar rule. If we have P or Q and we have the right-hand side disjunct, well, actually the negation of the right-hand side disjunct, then we can conclude the left-hand side disjunct. These 2 rules are reasoning for reasoning from top to bottom. If we know a disjunction, then we conclude, and we also know the negation of one of the disjuncts, then we can conclude the other disjunct. So that's for disjunction, and now I realize that I'm missing one rule here, and that is for disjunction introduction. Apologies for the messy going back and forth of the slides. So suppose that we want to prove a disjunction. We want to prove that P or Q is true in a particular context. How can we proceed? Well, of course, it would be sufficient to simply prove one of the disjuncts, but actually there's a more powerful method that we can apply. So the more powerful method says, okay, it's not, you don't just have to prove Q, you actually may prove Q assuming the negation of the other disjunct, assuming not P. So also disjunction introduction gives rise to a flag, an extra assumption that you may actually use to prove Q. right? And similarly, we have the symmetric version of disjunction introduction. If you want to prove a disjunction, you can also assume the negation of the right-hand side disjunct and prove the left-hand side disjunct. And if you manage to do that, you have established the disjunction. As I said, we're going to do an example soon explaining these rules in more detail. Let me show you also two rules for by implication. They're actually straightforward. They're basically making use of the fact that a by implication is the conjunction of two implications, as you see over here. So P implies Q and Q implies P. So from these two statements, actually, you can conclude the by implication. So if you want to prove that a by implication is true, then it is enough to prove both implications, right? It's enough to prove, and this is a typical method to prove that you have a by implication, prove the two implications separately. For using a by implication, well, you can use it in two ways. Again, we use that from the by implication, both implications follow. So if you have somehow established a by implication, then you may conclude the left and the implication from left to right, but you may also conclude the implication from right to left. Okay. What I want to do is give an example, and what I want to prove is actually that this sort of complicated looking formula is a tautology. And again, you could start making a truth table that's quite cumbersome and gives little insight, but a derivation gives a clearer argument, and it really reasons about the meaning of these constructs. All right, let me show you my blackboard, and I'll copy then, and I'll start the derivation. So what I want to prove now is the formula. Oops, wrong color. So, what's going on? There we go. We have the by implication, P by implication Q implies P and Q, or not P and not Q. This is our goal, and the first thing we always do is look for the main symbol in our goal, and that is an implication. So, and I don't have to show you the rule again because you by now have seen it a couple of times. If we want to prove an implication, it always goes like this. We assume the left-hand side of the implication, and this is in this case that is P by implication Q. And from this assumption, we want to establish, or we want to derive with an application of, so we want to derive the following goal. We want to prove that P and Q, or not P and not Q follows. This is the right-hand side of the implication that we write over here. And if we manage to do that, we apply implication introduction on line 1, which is over here, and some line that I don't know yet. So and then of course I get a flagpole that indicates that this assumption is made, this P by implication Q is made for the purpose of establishing actually this goal, and actually for the purpose of establishing this implication, and therefore its validity ends as soon as we do the implication introduction. Okay, so now we need to prove this disjunction. So let's have a look at the rules for disjunction that we have at our disposal. Let me. I have them here. I think, is this the one? No, this is not. Now I have to look for it, I'm afraid. Yes, this looks more like it. Well, maybe it was right after all. Let me show them both. So these are the two rules for proving a disjunction. So if you want to establish a disjunction, then you have basically two possibilities. There are two rules that you could apply. Either you could decide to actually assume the negation of the left-hand side disjunct and try to prove the right-hand side disjunct, or you can assume the negation of the right-hand side disjunct and prove the left-hand side disjunct. Okay. Well, we don't know we don't know at this stage which is best. So it may be necessary to backtrack. What I'll choose to do here now, basically, also, well, this is just an educated guess, but I want to prevent too many negations here. So if I would apply the rule that actually would put the negation of this thing in a flag, then I get basically double negations. That's usually not a good idea, but we don't know this for sure. It's a matter of trying, and maybe we have to decide at some point that we get stuck and that we have to backtrack and that we have to, in the end, apply the other rule. So what I'm going to do is apply negation introduction using actually this rule over here. So I'm assuming the negation of the left-hand side disjunct. So there we go. I say assume, and then I have the negation of the left-hand side disjunct, so that is not P and Q. And this so we added that basically to the context, and then at the end I want to do disjunction introduction on lines 2 and, well, this other line I don't know yet, so that will be on line 2. And so what is my goal now is the right hand side disjunct. So this is what I need to prove. Okay, so I write that goal over here. I want to prove that not P and not Q. Now, if we want to establish a conjunction, then to prove a conjunction, we should prove the conjunct separately. So we should basically prove not P and not Q, and then and basically the rule for conjunction says that we should do this separately. Let me in the meantime also check the questions in the chat. So do you have to write assume explicitly every time? Isn't that already implicitly stated there by using the flagpole? And the answer is yes. If you omit assume, that is okay, but that is basically everything that you can omit. So don't in particular omit things like mentioning the rule, and don't omit the flagpoles, don't omit the flags. They are all part of the formalism. The assume, I agree with the person who asked the question. The assume at some point is a bit superfluous because you can already see that there's an assumption because it's in a flag. All right. Okay. So we continue, and now so we want to do a conjunction introduction, and basically this conjunction introduction rule says, okay, to prove a conjunction, what you need to do is prove both conjuncts separately. So let's now focus first on. So there's a proof required here, derivation required here. Let's mark that for now by putting a couple of dots over here and make sure that we have enough space to actually write the other goal. So now let's first focus on proving not P. In the meantime, I'll check the chat. When you have a negation in front of not P and not Q, then the negations would cancel. Could you therefore write P or Q in the flag? Good question. No, and the answer is no. We are making a derivation here, and that means that we are limited to applying derivation rules. So even if you know that some formula must be equivalent to some other formula, it's not allowed to replace this formula by the other formula. So in particular, if you have somehow in your flag not P and not Q, then you cannot replace it by not P or not by P or Q. Not okay. So stick to the rules, the derivation rules, and that's the only tools that you can use here. Let's focus on actually proving this goal not P here. And the goal not P, let me see, yeah, the goal not P, to prove that, we apply a negation introduction on 3 and some other place. So And a negation introduction will again generate an assumption. We assume P, and our goal now becomes to derive a contradiction. And maybe just to comment a bit more on why you should stick to the derivation rules, what we're trying to teach you here is to stick to give a proof in a particular formal system so that you get well acquainted with these derivation rules. And this will pay off later. Because you're very fluent in this style of reasoning, then giving proofs later will be simplified. You will not have to think about too much about the logical reasoning. If we would allow you to apply all sorts of apply all sorts of equations, equivalences actually in a derivation, then the focus would not be on learning how to apply these rules. It will pay off. Trust me on this. So we were here. We wanted to derive a contradiction actually from what we have in the context. And the context actually says that, we have a by implication, P by implication Q, we have not P and Q, and we have P. So the question now is, how do we get our contradiction? And now, basically, we should start to, before we actually write down the derivation, we should start to think about this a bit. Note that if you have P implies Q and also P, P by implication Q and also P, then by the rule for by implication elimination, you can turn this into an implication. I'll show the rule in a bit. And then you also get Q. And so if we have P and Q, then we can conclude P and Q, and then we have a contradiction with this formula over here. Let me show you the rule for by implication elimination. I think we can now make the rules for disjunction. We can make them into make them smaller again. Let's check the rule for by implication elimination. No, that's the introduction rule. So the rule for by implication elimination says if you have a by implication, P by implication Q, then you can conclude Q implies P, and you can also conclude there's this other rule. I actually need the other rule here, where you can actually conclude P implies Q. I think I don't have that rule over here. So let's do that first. We do a by implication elimination on line 1, and this will yield P implies Q. This is line 3, this is line 4. And now from P implies Q, we can do an implication elimination because we have P and we have the implication. So with an implication elimination, on 4 and 3, we can conclude Q. And now, since we have both P and Q, so we have P and we have Q, we can do a conjunction introduction to conclude. So this is on 3, and this will be line 5. We can do a conjunction introduction. We get P and Q, and now we have our contradiction. This is line 6. Now we have our contradiction because we have P and Q, but we also still have in the context not P and Q. So we have a formula, P and Q, and its negation, not P and Q, right? So we can conclude our contradiction by an application of negation elimination on 2 and 6. So that will be on line 7. And so this will also be referred to line 7. Now this is only part of the derivation. There's still this hole in my proof that I should fill also with derivation. I'm going to skip that here. It is in the video that is posted. So you can also, and actually it's very similar. It uses exactly the same strategy as we have used here, only we use the other elimination rule for the by implication. So we use Q implies P instead of P implies Q, and then for the rest it's basically the same. Right, so seeing this, if you understand this, you will also understand the proof or the derivation of not Q in this context. All right, let me see whether there are still questions remaining in the chat. When you have a negation in front of, oh, so we have already dealt with that one. So another question is, why did we get this not P and Q in a flag? That is a good question. So let me go back to that. So we're actually doing a disjunction introduction here. We have a disjunction that we want to prove, and then there is this rule for disjunction introduction. Let me show it to you. I hope it's this one. Yes, it's this one. So the rule for disjunction introduction says, well, if you want to prove a disjunction P or Q, then what you can do, a strategy to do that is to assume the negation of the left-hand side disjunct, and then your new goal becomes to prove the right-hand side disjunct, right? And that's exactly what we've done here, because we had a disjunction here, and this was the left-hand side disjunct. So we assume the negation of the left-hand side disjunct and try to prove, and actually almost succeeded, to prove the right-hand side disjunct. That's what's going on here. Then there's a couple of more questions. I think I can now, well, oh, there's a question still about this derivation. So let me try to answer that one, referring to the derivation. I think I remove the rule again. So looking at the stream, I noticed implication elimination on 4 and 3. Does the order matter in which you write down the numbers, or does it not matter when being graded during the test? The answer is it does not matter when if you interchange the rules. You're referring actually to this place over here. I really stick meticulously to the way the rule for implication elimination is formulated. It mentions the implication first, and so that one appears on line 4, and then the left-hand side of the implication, which appears on line 3. But if you interchange 4 and 3 here, that is not such a big deal, because we can see which of the two is the implication and which of the two is the left-hand side of the implication. So don't worry about that. But strictly speaking, this is the way it's formulated in the rule. And why am I so pedantically doing this? Well, I think this is what you should do too. You should try to apply these rules as precisely as you can. That will give you the best results, and also because typically in the beginning you cannot judge which variations on this thing are allowed and which are not. Okay, so I urge you to try to apply these rules as precisely as possible. Especially if you do the first couple of exercises, make sure that you have the rules close and that you can all the time look at the rules to see whether you're applying it correctly. All right. Then there is a question that I think is not really related to what I just showed. So let me answer that question. So the question is, can we use LaTeX? The answer is simply yes. Well, I sort of stimulate the use of LaTeX, but it will take you too much time, in particular on tests. And I think also when doing solving exercises to typeset all these things in LaTeX. I'm pretty skilled in this by now after 10 years of typesetting flag style derivations, but you get the hang of it. But it will take you too much time actually to produce flag style derivations in LaTeX. I think there is a package that is called FlagDeriv. That you might use for that if you are really keen on learning how to make flag style derivations in LaTeX. But as I said, I suggest that you first that you do the exercises just using a pen and paper. In fact, whenever I make a flag style derivation in LaTeX, I always first do it on paper, because only then I can properly typeset it in LaTeX. So I hope that that answers your question about LaTeX. Last question, and then we call it a day. should we skip chapter 10? We are skipping chapter 10 here in the lecture, and we also did not do any exercises about chapter 10 or from chapter 10. But I suggest that you read chapter 10 in the book. It gives you some extra information about binding. We're not going to see a lot of binders. Chapter 10 discusses a couple of binders like the existential and the universal quantification. So for instance, the sum binder, well, that one we will encounter later in the course, but there are a couple of others that we'll not see in the rest of the course. So it's sort of a bit outside the scope, but it's helpful to read it just once, and maybe and we'll get back to that towards the end of the course. When we do induction, then at least the summation will return. Okay, ladies and gentlemen, I realize that I will definitely think about how to sort of reduce the pace of the lecture. I hope the second part was a bit better because I did these examples on my iPad to slow down a bit the explanations. I hope you'll watch back the videos when they're posted, and well, they are already posted in Canvas. And then, there's one thing that actually Peter tells me, but I don't understand what I should do with that. So maybe he can explain this a bit further. There's one other thing I'm going to do. I'm going to do a short poll in Canvas later this week. I would appreciate if you could fill it out. I'll just ask you a couple of simple questions about how we could perhaps improve the way this course is taught. We would be happy to hear your opinion there. There's one last remark that especially Peter tells me to make, and that is that you should prepare, and I think you should prepare for everything. You could prepare for the lecture by, for instance, already watching the videos before the lecture. I'll make sure that they are posted well before, a couple of days before the lecture actually. I'll do that as soon as possible so that you can already watch the lectures, but you should also prepare for the tutorials by trying all the exercises on the program. In this way you will benefit most, because then you have already thought about the difficulties of the exercises. The tutorials will become more efficient, but also you'll get a better appreciation of what is difficult and what is not. All right. I thank you for your attention for this second lecture, and I'll see you again next week or next Wednesday with another lecture. Good luck with the tutorials and the test at the end of at the beginning of next Wednesday. Bye bye.